So today is our third lecture of electric circuit analysis 2, and in the last lecture we saw about the voltage and current relationships of different circuit elements like resistors, inductors and capacitors. And we saw that the capacitor and inductor, there is a phase difference of 90 degree between voltage and current. In case of capacitors, the voltage lags 90 degree behind the current, and for pure inductor the current lags 90 degree behind the voltage, and for pure resistor there is no difference between voltage and current in terms of phase. So, and these are the final relationships between between the voltage and current for different circuit elements, resistors, inductors and capacitors in time domain and frequency domain. So today, just starting briefly with a small example. Voltage of 12 cos of 60t plus 45 degrees is applied to the inductor of 0.1 Henry, and we need to find the steady state current through the inductor. So the word steady state is used for trivial reason now, because in Phasor domain we do not consider the initial conditions when taking the integrals or derivatives, and in the end what the derivative and integral in Phasor domain result in, they only contain the information about the steady state. That is, when we take the derivative we just multiply j omega, or when we are taking the integral we are just dividing with j omega, and there is no information about initial conditions, so this result is for the steady state operation. So for that reason it is mentioned here the steady state current. So as we know that for inductor the voltage is j omega L times I, so and omega is 60 from this relationship, and voltage can be simply written in Phasor form like the 12 angle 45, because this expression is given in cosine function. If it is in sine function, then we have to take the respective phase angle difference by converting this sine to cos function, and then 90 degrees here, subtracting 90 degrees, and in the end we would have got the exact expression which can be converted into Phasor. But now here, because the given function is in cosine, so we need not to worry about this conversion, and we can directly write the voltage as 12 angle 45 degrees. So, and because from this relationship we can simply derive that current is voltage divided by j times omega times the inductance. So simply putting the values, we get the inductor current as 2 angle minus 45 degrees, and when we convert it back into time domain, the expression would be 2 times cosine of omega t minus 45, and as we know omega is 60 degrees, so we write 2 times cos of 60 t minus 45 degrees ampere is the current flowing through inductor in steady state condition. Moving on to the next topic, the impedance and admittance. We have seen that the voltage and current relationships for different circuit elements in our previous lecture. So, and ratio of the voltage and current is actually a resistance. In case of pure resistive load we call it resistance, but for inductive or capacitive loads we call this term as impedance or reactance. If there is only capacitive or inductive parts, then we call them reactance. We are going to see these details in coming slides as well. So what we have to look here is voltage and current ratio is R. Voltage and current ratio for inductor case is J times omega L. Voltage to current ratio in case of capacitors is 1 upon J omega C, or minus J upon omega C can also be written. So from these expressions, what we deduce or what we derive is that voltage upon I can be R or J omega L or 1 upon J omega C, and as a combination we use the term Z for this. From these expressions we obtain the Ohm's law in phasor form like this one, or voltage is equal to Z times current phasor, where Z is a frequency dependent quantity, because Z is generic term which can be R, which can be J omega L or 1 upon J omega C. So when we have this omega expression term here, it means that it is frequency dependent, and although we measure this term in ohms, it is frequency dependent and it's called impedance. The impedance Z of the circuit is the ratio of the phasor voltage and phasor current, as we have just seen. It is measured in ohms, and impedance represents the opposition to the that circuit exhibits to the flow of sinusoidal current. So previously we defined resistance in case of DC circuits and DC quantities. We were defining it as an opposition, as an hurdle, as an you can say objection to the flow of DC current, and because that is only a pure resistive part, then we called it resistance in that case. Here it is to the sinusoidal case and we call it impedance. And mentioning sinusoidal is also important because it is frequency dependent quantities, and for DC quantities we do not have any frequency. Although the impedance is the ratio of two phasors, it is not a phasor. This is an important point to consider, because in case of phasors we have to the given function must correspond to some sinusoid, but impedance is not a sinusoidally varying quantity. It is a constant quantity for given frequency. It is frequency dependent. For frequency f1, let us say it has the value of z1, then it would remain z1 for all the you can say amplitude values. But if it is we are working at frequency f2, then its value will change, but it is not sinusoidally varying. It is somehow constant quantity for that given frequency. So we do not call it as a phasor, although it's dependent upon the frequency. So the capacitive impedance Zc is equal to minus J upon omega C. It is same as 1 upon J omega C. Just mathematical manipulations to convert 1 upon J omega C to minus J upon omega C. And for inductive impedance, ZL is the symbol used here, and we can say it's equal to J times omega L. Consider two extreme cases for these two impedances. For example, when we consider omega equal to 0, the capacitive impedance would be infinite, and inductive impedance would be 0. So this shows that for pure DC input signal, when the angular frequency is 0, the capacitor would act as an open circuit and the inductor would act as the short circuit. This is shown here. Inductor will act as a short circuit at DC, and the capacitor will act as open circuit for DC. Moving on to the next extreme, that is where angular frequency omega is very high, then the we consider it as infinite, then putting infinity here, ZC would result to 0 and ZL would result to infinite. So this indicates that the inductor will act as an open circuit for very high frequencies, whereas the capacitor will act as the short circuit at high frequencies. So because this impedance quantity is a complex quantity, we can have often in the circuits the combination of both capacitors, inductors, or resistors. Any combination, any 2 or 3 of these elements can be present in a circuit. So often we have to deal with this complex number. These quantities for ZC and ZL are imaginary numbers. We have that J operator with them, whereas with resistors there is no imaginary operator, so it is a real number. And when these two elements, resistor or capacitor, or resistor and inductor, come in series or parallel, the resulting impedance would be combination of both. So it would have some real part as well as some inductive part. So to highlight that thing, what we use is, as a complex quantity, the impedance may be expressed in rectangular form, or resistive plus inductive or capacitive part. This R is the real part of Z is resistance, and X as an imaginary part of Z is reactance. So impedance is the term which can be used for this whole combination, which carries both real and reactive parts. The real part is resistive, whereas reactive part is due to capacitor or inductor. X can be positive or negative. Positive for the inductive loads, as we can see from this previous relationship. For inductive loads, the impedance value is positive, whereas for capacitive case, the impedance values is negative. So here, if X is positive, then we call the whole load as inductive load, and the power factor would be lagging, whereas for negative X value, it indicates the capacitive load and power factor would be leading, because current leads the voltage in that case, as we have seen in our previous lecture and today's slides also. The impedance, resistance, and reactance all are measured in ohms. Whether you measure resistance, it's in ohm. Whether you measure capacitive impedance, reactance, it's in ohms. And whether you measure inductive reactance, it would be measured in ohms. Or if you measure the combination of both, it would be in ohms. Impedance and admittance. The impedance may be expressed in polar form because it's a complex number, so every possible representation expression for complex number also applies here. So we can express them in polar form, in rectangular form, or in exponential form. Anything and any conversion can be done like the complex numbers. So if we have to measure the magnitude, it's just the square of real part plus square of the imaginary part, whole under the root would be its magnitude, and for angle it would be tan inverse of imaginary part upon real part. Or if you are given in polar form, then you can convert it into rectangular form using these two relationships. These relationships are not new, these are just old relationships which we have always been used in complex number analysis manipulation. So moving on to the next, the admittance thing. Admittance is converse of the impedance, reciprocal of the impedance. So if Y is impedance, then it would be equal to 1 upon Z or I upon V. And as we know that Z has the real and imaginary parts, obviously the admittance would have also the real and imaginary parts. So the common convention for most of the writers is that we represent admittance as G plus J times B, where G is a real part of Y and is called conductance. It corresponds to resistance, but it is not equal to 1 upon R. We have to just see into its details. And the B part is called susceptance. It is imaginary part of this Y admittance. G, B or Y, all these quantities are measured in Siemens or moles. So G plus J times B is 1 upon Z, so 1 upon R plus J times X, and by rationalization we can get the real and imaginary parts as this one. And you can see from these relationships that conductance is not equal to 1 upon R, as I earlier mentioned. It can only be equal to 1 upon R if there is no X part, no reactance part. If reactance is 0, then you can say its conductance is equal to 1 upon R. Otherwise, it is not equal. This is very important, and one must keep in mind always to get avoiding the troubles while solving the problems or looking at the circuits. And secondly, the susceptance part, B is equal to minus X upon R square plus J or R square plus X square. So these quantities, both these quantities are not direct reciprocal of resistance and reactance. So we must consider these things in mind. So as a final conclusive slide, this shows that the impedance is equal to R for pure resistive load and admittance is 1 by R for pure resistive load. For inductive load, impedance is J times omega L and Y can be seen as 1 upon J omega L. Keep in mind, this is for pure inductor. There is no resistive or capacitive parts. And for C, for pure capacitor, Z is 1 upon J omega C, or admittance is Y is equal to J omega C. Once again, one must keep in mind that this is for pure capacitor. There is no inductive or resistive impedance present in the circuit. Only in that case we can say Y is J omega C. Otherwise not. Otherwise we need to calculate the admittance using these relationships given here. Moving on to some examples of this voltage and current analysis. Find the voltage and current in this circuit. There are two elements, resistance and a capacitance. For given voltage, we can see that omega is 4. With this omega information and the amount of capacitance 0.1 farad, we can calculate the capacitive impedance XC, for example, which would be 1 upon J omega C, 1 upon 4 J times 4 times 0.1 as mentioned here. Now these two impedances are in series, so just add them and we will get 5 minus J times 2.5 ohms. This 5 correspond to this resistive part, the real part. This J correspond to the imaginary part, which is due to the capacitor. So now solving this problem is pretty much easy. In Phasor domain, for example, we need to find the current in the circuit, which would be voltage source voltage divided by the impedance of these series elements. So source voltage is nothing but 10 angle 0, because we have nothing in addition to omega t as the angle of cos. So it would be 10 angle 0 divided by 5 minus J 2.5, which we just calculated here. After mathematical manipulations, we can get Phasor current as 1.7 at 9 angle 26.57 amperes. And in order to get the voltage drop across the, for example, capacitor, what we need to do is just multiply the current flowing through the capacitor with its impedance. This is what we are doing here. I is Z times C. So putting the values, and we can get it's 4.47 angle minus 63.43. V is the voltage across the capacitor. So when we want to convert, because in the question we are given, we are asked to find V of t and I of t. These are not Phasor quantities, these are time dependent quantities. So we must write our answer in time domain. So I of t would be 1.789 cosine of 4t, because we are given 4t here in place of omega t. 4t plus 26.57 as given here. Similarly, the voltage would be 4.47 cosine of 4t minus 63.43 degrees. Notice that the current and voltage are 90 degree of phase difference, 26.57 and minus 63.43. For example, if we want to draw their phasor diagram, what would we do? This is our x-axis and y-axis. For example, we want to draw the phasor diagram. This is real axis, this is, let us say, imaginary axis. What we see, the current is at plus 26.57 degrees. Positive angle is always measured in counterclockwise direction. So this is the current, phasor I. Its magnitude is 1.789, rounding off 1.79, and the angle is 26.57. And if we want to draw the phasor of voltage, it carries negative angle. So with respect to our reference point, it is in counterclockwise direction at minus 63 degrees. So what's that? It's like this one. We are measuring our angle in negative direction, and it would be minus 63.43. Right, and its magnitude of this thing would be 4.47. So the angle between voltage and current is 90 degrees, where voltage is lagging behind the current by 90 degrees. Or conversely, we can say the current is leading the voltage by 90 degrees as mentioned here. So in this way, we can simply draw the phasor diagrams if asked in any of the questions. So moving on to the next topic, Kirchhoff laws in the frequency domain. For example, consider V1, V2 up to Vn are the voltages around the closed loop, are the series elements connected in series. The voltage drops across them is V1, V2, so on. So according to the KVL statement, sum of all the voltages in a loop is 0. And as we are operating in AC sinusoidal quantities, V1 would be Vm1 cos of omega t plus theta 1, V2 would be Vm2 cos of omega t plus 2, and so on, Vmn cos of omega t plus theta n. And by taking their real parts and trying to represent them, because we are trying to represent these sinusoids as phasor quantities, the same operation we did in our first and second lectures is that we represent them as Euler quantities and then separate the time dependent portion from the phase angle. So this would be our phasor. And because we are representing in phasor domain, so we are just omitting these parts. So doing the same operations as we did in our previous lectures, we reach this expression. Now that this part cannot be equal to 0, this is some positive or negative. Time can never be 0, it's something positive. So, and omega frequency can also be some positive value. So usually this expression cannot be 0. So this would be 0. And it shows that the KVL, Kirchhoff voltage law, is also valid in phasor domain. Using similar set of operations, we can say that the Kirchhoff current law is also applicable in phasor domain. Many things such as impedance combination, nodal and mesh analysis, superposition, and source transformation are easier to solve in frequency domains because we are operating in phasor domain. We have simple mathematical transformations, additions for subtraction, addition, multiplication, and other mathematical or trigonometric operations we can perform comparatively easily in frequency domain. So all these analyses are preferred in frequency domain. So impedance combination, if consider there are number of impedances connected in series, then voltage of the supply would be equal to sum of all the voltages. Voltage drops across all the elements V1, V2 up to Vn, and it can be written because it's series, all these are series elements, so current would be same and impedances would be added, and this way we can say that equivalent impedance is sum of all the impedances in phasor domain as well. Similarly, considering two elements in series, we can derive the relationship for voltage division as we did in DC analysis. The current through the series element would be V upon Z1 plus Z2, and V1 would be, because it's current, V1 is Z1 times I. Putting the values, we get these relationships very simply, and these are nothing but the voltage division relationships as we did in DC analysis. Only we were using R instead of Z there because the inductive or capacitive elements had no significance there. We were treating them as a short circuit or open circuit. So this is similar kind of relationship. For the current division principle, we can take the sum of all the currents flowing through different branches is equal to sum of the input current. At this node, current entering the node is equal to current leaving the node. This is also the statement of Kirchhoff current law. So putting the values and then transforming these quantities by simple mathematical operations, what we get is I1 is equal to Z2 upon Z1 plus Z2, and I2 is equal to Z1 upon Z1 plus 2 times the total current I. These relationships are current division relationships. Moreover, another important point which is mentioned here is about the admittance. For such type of circuits, for this type of circuits, the equivalent impedance is equal to the sum of all the impedance as we do in series case. For impedance, equivalent admittance is equal to sum of all the admittances connected in parallel, as we do in case of impedance for series circuit. We can do for admittance in parallel circuits. Now the delta and Y transformation. For example, we are given some circuit in delta form and we need to find or convert it into delta configuration. So Y to delta transformation relationships can be used. These relationships, such relationships were derived also in case of DC analysis. Only difference is the representation of resistance and impedance. There we were only working with resistance, so we used R1, R2, R3 and RA, RB and RC. While here we can use Z1, Z2, Z3, ZA, ZB and ZC for different impedances. Similarly, converting back from delta to Y is also possible using these relationships. However, it is important that for most of the loads, in practical cases, for example in power systems, we usually prefer the balanced load, which means that the load in all the three arms of Y or delta is similar, same in magnitude and angle. So that's why we can use Z delta as 3 times ZY. For example, as if for the balanced network, Z1 is equal to Z2 is equal to Z3 and ZA is equal to ZB is equal to ZC. So Z1, this would be, the numerator would be 3 times Z square divided by Z. So Z is cancelled with this one term and 3 times Z would be remaining. Similarly, for here it would be Z square divided by 3 times Z. So 1 of the Z would cancel and Z upon 3 or 1 upon 3 Z delta would be the answer. So for all these derivations which we have just seen in previous 6-7 slides, the conclusion is that every operation that was possible in DC analysis is also possible in AC analysis, and especially in Phasor domain we can also do that. So principle of voltage division, current circuit reduction, for example series parallel combinations and impedance equivalence, and everything that applies in DC circuit equally valid and applies to the AC circuits. There are some examples. For example, find the input impedance. So we have to find an equivalent impedance. We can just see that these two elements are in series. Omega is given here, 50 radians. So we can convert this inductance into an impedance. Similarly, these two elements are also in series. Omega is also given. So this capacitive impedance can also be found, and here the capacitive impedance is also easily found. So in result there would be 3 elements. These, for example, we call it Z1, we call this one Z2, and this one is Z3. So now Z2 and Z3 are in parallel. First find their parallel combination and then make the resulting impedance in series with Z1. This is what is done here. First it has the impedance, equivalent impedance is found for 50 radians per second, and then Z1 is in series with the parallel combination of Z2 and 3. So the end result would be 3.22 minus J11.07. So what we can see or conclude from this expression, the overall circuit is capacitive or inductive. From real part we see that there is some impact of pure resistance. From imaginary part, due to this sign we can find out whether the impedance is inductive, net result is finally equivalent impedance is inductive or capacitive. So negative sign is used for capacitor impedance as we have earlier seen. So the whole idea is, or whole result is, that Zin is capacitive impedance. The power factor would be leading in this case. Excuse me. Moving on to the next example, find V naught of T. V naught is the voltage across this inductor. So we can use simply the basic current, basic voltage analysis, circuit analysis principle in order to find this one. From this relationship Vn, we can see that omega is 4 and its phase angle is minus 15, because expression is given in cosine as a cosine function, so we can directly convert it into Phasor domain. 20 angle minus 15, omega is 4. Impedance for 10 microfarad capacitor is found, then impedance for 5 Henry inductor is found. These two are in parallel, so we find their parallel combination, and then a simple voltage divider between 6 ohm and the parallel combination of these two would result in the output voltage. Because these two elements are in parallel, so whatever the voltage across the parallel combination is also the voltage across 5 Henry inductor. So the final result is V naught 17.515 cosine of 40 plus 15.96. In Phasor domain it's given like this one. The last example for today, find current I in the circuit of figure 9.28. This figure number is with respect to the fundamentals of electric circuit analysis by Alexander and Sadiku. In this example we can see that there is a Y network between or among nodes A, B and C. This branch, and these branches in combine make a delta, or we can see A, B and these branch make a Y combination. So there can be different possibilities. Students can practice this example on their own for different possible combinations. We can also see a delta here, this combination of these two and this one. So what we have considered here is we need to find the equivalent circuit, and then using the same relationships on previous slides we can just simplify this circuit. We obtain the Y impedances as follows: ZAN is equal to 4 times 2 minus 4j. 4 is this one, 2 minus 4j is this one, and divided by the sum of all three impedances. 2 minus 4j, 1 impedance, the second is 4j, and third one is 8 ohm. Similarly for ZBN, we can multiply 4j and 8 ohm divided by sum of all these, and sum of all these is 10 from previous. Similarly for ZCN, and in this way the circuit would result like this. Now ZCN is in series with 6j and 8 ohm. ZBN is in series with minus 3j, and ZAN is in series with 12 ohm. After finding these series combinations like this one, this series combination is in parallel to this one. We need to find the parallel combination afterwards, and after that we can see we can find the current by simple relationship, voltage divided by impedance. So after finding the parallel combination of these two, all these impedances would result in series combination, so we can find them. With this I close today's lecture, and we reach the end of chapter number 9 of our textbook Fundamentals of Electric Circuit Analysis by Alexander. Student can try at home the conversion from different other perspectives. As I mentioned, we have a Y combination here also, we can have a delta combination here also. So what would be the result? Theoretically the result would be similar, there should not be any difference in the final result. However, whatever method or route we follow to reach this final destination. Thank you very much. See you in next lecture.